Hello everyone, thanks for joining me today. My name is Richard Barry. I am best known as the original author of FreeRTOS. I'll tell you what that is in a little bit. I currently work as a senior principal engineer for AWS IoT. That is Amazon Web Services, Internet of Things. And I work, of course, on the devices, the things that connect to IoT. And I very much still work on FreeRTOS, in fact. Today, though, we are going to talk about future-proofing your embedded software designs. Now, why is this important? Well, basically, embedded software is getting more complex. As the price point of devices comes down, we're putting more functionality on those devices, larger integrations, and this is going to, over time, get increasingly more complex, especially with things like IoT, where, as I will show, we have integrations of libraries that we have to manage. So as things get more complex, then obviously our development costs may go up. And to ensure we get a return on investment on that development, we want to make sure that our products can stay in the market as long as possible. And this is what I call future-proofing. Make sure that as we add new products or update existing products, we can do so with as few changes as possible. So I'm going to talk a little bit about different options we've got for taking these increasingly complex embedded products to market. And then also we'll look at the criteria that we can use to judge kind of how future-proof our designs are, or our choices are. Now, I've worked on FreeRTOS for about 18 years. I normally show this diagram to kind of demonstrate the growth in the number of downloads of FreeRTOS over those years. It's downloaded about once every 170 seconds at the moment. Now, I've augmented this with a little bit more information here, and it's worth pointing out here that FreeRTOS is a small system, okay? Itself requires about, roughly 10 kilobytes of program space, and it requires a few bytes of RAM, tens of bytes of RAM. Typically, an application that FreeRTOS gets used in would be a few hundred to a megabyte of program space and a few hundred kilobytes of RAM, but this very, very broad spectrum. So that's just like the average. And what I've put on this chart here is you can see that on the left-hand side, when we first brought FreeRTOS to the world, first published it on the internet, we were really working on 8-bit devices doing simple task switches. And as we move along that x-axis through time, you can see it wasn't long before we were working on more complex multi-core projects, and then went through 32-bit to 64-bit ARM cores, 64-bit RISC-V cores, and then now IoT. IoT is the big growth area, and this brings with it more complexity. I can demonstrate that with an example, and this is designed to be something which is small but very sophisticated. So this is our starting point. This is a disconnected motor, but a very sophisticated motor. The algorithms used to control the motor give it a very high fidelity. Now, this is a small piece of software. Maybe we just need one software engineer. So I'm showing one software engineer here. Let's call her Margaret. She's a good software engineer. She's a good mathematician. She's doing something clever. I'm trying to demonstrate that something clever by those sine waves. Doesn't really matter what it is, but it's sophisticated. And then we're ending up with this, motor with very, very high fidelity control. What is required to do this software-wise? Well, actually not that much software. So I'm kind of representing that with this diagram here. And this is trying to show that most of that software is application software. There may be drivers that we're using to access PWMs or libraries like fixed point math or something like that. Maybe there is, maybe there isn't. Very little software though, predominantly because the algorithms used, although they're sophisticated, are small, right? That's why I said small. Maybe it's even written in assembly. This kind of application, it would typically rely heavily on interrupts, very fast interrupts coming from motor sensors and timers and that kind of thing. Now, let's say our motor is very successful and we want to plow on into the market. We want to really add value. And one of the ways we can add value is through predictive maintenance. Predictive maintenance effectively means that the motor is monitored and we learn how the motor behaves, and then we can determine when the motor is starting to misbehave and then predict it going wrong before it goes wrong. Now this means your customers will be delighted because you are saving them downtime. You can save a lot of money because rather than having to do scheduled maintenance regularly, then you can monitor the motors and just send out an engineer when something actually needs to be done, or send out a replacement when something actually needs to be done. Now this kind of functionality, very high value functionality as I've just described, typically is done by sending data to the cloud and having the cloud run the algorithms. And of course, if you send all the data to the cloud and you store it all in one place and in one format, you can actually get much greater insights in there as well. You can compare how different motors are performing and hopefully just improve the efficiency of your entire fleet of motors. So very high value. I should explain this diagram, because it's a little complex. On the left, that hexagon we have outside of the cloud. This is where our devices are. So this is where our motor would sit. And it's then going to send data through that little cloud icon with the door in it, which is the gateway to the cloud. Now it may send all the data, or it may do some processing outside of the cloud, to filter and clean the data, and then just send the pertinent data to the cloud. It wants to get that data to the far right-hand side. All the rest of that diagram is inside the cloud. You look at the far right-hand side, that's where the analytics is. That's where we can do things like machine learning, etc., etc. And that's where we're going to add value to our product. But you can see to get from the left outside the cloud to the analytics on the right-hand side of the cloud, there are lots of other icons we are going to go through, lots of other little pillars of functionality. Now this is what we call undifferentiating functionality. It's not adding to your business logic, it's not doing anything for your predictive maintenance, but it has to be there in order for you to benefit from that predictive maintenance. These are things like the protocol implementations, security, encryption, authentication, fleet management, fleet onboarding, over-the-air updates, etc., etc. Now, as an embedded engineer, you're not going to have to do or have to do any of that stuff. And that's provided for you by cloud services like AWS IoT to make sure that you can get to the value as quickly as possible. You don't have to learn that stuff as well. And if we look at what happens when we internet connect our motor, you'll find it's exactly the same. Now we've kind of transformed our very simple motor software from the left to the right. You can see we've got those protocols. We've got the TCP, we've got MQTT, which is another IP-based protocol. There we've got the transport interfaces with Wi-Fi, TLS, which is, this is the encryption and authentication. We use this all the time when we connect to an HTTPS server in your browser, whether you know it or not. Because of the authentication, then we have to have secrets management. We have to have private keys and certificates, so you can authenticate that you're connecting to the correct cloud, and the cloud knows that you are authorized to connect to it. So you can see here that there's all this undifferentiating functionality. It's also demonstrated on, this is just another view. This is showing the program space, the memory map of the program space, disconnected on the left, connected on the right. So you can see that the amount of application code has increased a little bit because we're doing this predictive maintenance. All the rest, though, is this undifferentiating functionality. So what we need to do first, before we think about the kind of future proofing, is just say, how do we manage this? How do we manage this complexity? And this is where just standard software engineering helps a lot, of course. And I think with all those connectivity interfaces and all those protocols where you have to manage the state and the retries and the timing and all that kind of thing, I think here we can justify saying that we need multi-threading. Of course, we don't need multi-threading, but we benefit from multi-threading because that make it more modular. We can encapsulate protocol management, the TCP management, the MQTT management inside their own threads, which we call agents or daemon tasks. That manages the whole protocol and gives you a very simple interface. It makes it, you can reuse those modules because you just get take the whole code for that thread and run it on different platforms. Etc., etc. Now, because I said this was a motor control application, we need to choose a kernel which will allow you to have these fast interrupts again. So without the kernel interfering with the introducing jitter. So systems like FreeRTOS manage this by only masking interrupts up to a certain level to implement critical sections to enable there to be that subset of interrupts which are not going to be impacted by the kernel. And then all the kind of connectivity can operate in tasks at a lower priority than that. So that's like the software engineering side of it. But then, where are we going to get all those libraries from? And here we have a couple of choices. We can either build that all ourselves, or we can acquire those libraries from somewhere else. If we acquire the libraries, then we have another choice. Do you want to buy those libraries in, or do you want to use open source? So on this diagram, I'm trying to show the kind of trade-offs here. So on the left-hand side, this is a timeline, okay? On the left-hand side, we have Margaret, our intrepid software engineer and math whiz, who used to do all this by herself. Now there are lots of additional protocols, there are integrations, there's lots more testing we have to do. We have to be able to understand how to patch the code, how to debug the code, etc. So inevitably we are going to need more people. Now, as we move along that timeline, we're adding more people to help Margaret with this task. Maybe these are people with expertise in security or something like that. And at some point, if we buy in the libraries or we use reference integrations, by which I mean pre-integrated and pre-tested integrations of all this undifferentiating functionality, we can go to market at a certain point. Maybe that's a choice we want to make. The other choice, of course, is to get all that expertise in-house. And so we can carry along the timeline, adding more and more people, writing more and more code, more and more testing, more integrations, more expertise, and eventually we can get to the market much later. But we've got all that expertise in-house. And maybe that's the best choice. You want to keep all that expertise for your business continuity. However, consider that most of this code that all those extra people are writing is the undifferentiating code. That means there's lots of other people writing the same code and testing the same code. So one of your options is, do I want to really benefit from all the work that other people are doing, or do I really want to spend my money replicating that? Because you can see our costs are going up, and also time to market is so critical these days. So to help us try and make these trade-off decisions, I've kind of identified these criteria. I've also split this criteria into two. The kind of orangey criteria are those which are going to help us get to market quickly. Because, unless you get to market quickly, then you don't really have to worry about your kind of longevity, your future-proofing if you're not in the market, right? So that's always got to come first. The more kind of greeny blue colors ones are really the future-proofing once we are in the market. And one of the things with build or buy, of course, if we look at, if we start with the business continuity there, one of the things with build or buy is, do you have access to the source code? Are your devices going to be in the market longer than the company selling you the source code, of course? So that's very important as well. Okay, so we can use these criteria to find the right balance. And remember, our objective here is to make sure that we can really benefit from the effort that we're putting into creating these products long into the future, not having to replicate anything. So the first thing we've already kind of mentioned, and this is the pre-tested reference integrations. And what that enables us to do is tick off the first items. This is the time to market. Whether you build it or whether you use open source, as long as it's pre-integrated and pre-tested, that will help us go to market. But then, of course, you have to choose which integration are you going to use. Now, FreeRTOS is one option, and if you go to the FreeRTOS website, there are a few other criteria that become kind of self-evident that we can tick off. One is the rapid support, so you can go to the FreeRTOS forum and see that the engineers working on the code and the community are providing very expert, very fast support. If you need a support contract, then we have partner companies that will provide that. Wittgenstein High Integrity Systems, for example, will be able to give you support contracts. AWS have various different tiers. I mean, if you are an AWS customer, of course, many people who use FreeRTOS are not AWS customers, but if you are, then there's various different tiered support levels there. And there's people like ProServe who will help you actually implement the code or get examples running for you as well. Then you can also see things like the wide ecosystem. You can look at all the history of the development code in the open source repositories and get an idea of how the IP is controlled. And very, very importantly, it's MIT licensed. This is an open source license, very enterprise friendly, very, very simple. Most enterprises will have it whitelisted already. Okay, so the next thing then is kind of a logical sequence here. If we are getting an integration from a single point, what do we have to consider for lock-in? Because to future-proof it, I don't want to be locked into any kind of ecosystem, be that cloud ecosystem or be it device ecosystem or tools ecosystem. So here, what we can do is make sure that we only use open standards. And if we look at this diagram again here, we can see that actually very, very little of this is not an open standard. Here we have OTA, which in this case is actually specific, or the OTA agent we provide is specific to AWS, but you can do OTA anywhere you like, and we'll talk about that at the end as well, to show that there's no real lock-in there either. But things like TCP, MQTT, TLS, completely open standards, so there's no real lock-in here. And if we look at things like how we are accessing the secrets on the devices, the private keys that we required for this mutual authentication, there again we use an open standard, which is the PKCS11 API. This enables you to access things like keys without ever exposing them in RAM. It's managed by Oasis, it's very broadly used. Incidentally, we only use a very small subset of it, so don't be worried when you look at the size of the protocol, or the API I should say, because it's used in things like laptops for authentication as well. So here we are making sure that we are using open standards, so we can say that there's kind of no lock-in here as well. But I think it goes beyond the protocols and the APIs. What about tooling, for example? Is there a particular source control that you have to use? Is there a particular package manager that you have to use, or a particular compiler? So I've already said that FreeRTOS actually supports many, many different compilers and many, many different architectures. We also manage this aspect of lock-in by making sure that we use very few tools, and the tools we use are probably the tools that you're using already. And very specifically, Git. What we've done over the last couple of years is take these libraries and make sure they're completely decoupled from everything else. So there's very, very little lock-in. Not only is there's no lock-in to FreeRTOS, because you can see here we do RTOS agnostic packages as well. The green is kind of packages that we provide. But there's no dependency on multi-threading even. So you can choose to use what we call the core library, so we've branded core MQTT, for example, or you can choose to use it with an agent, and the agent then is the thing that manages that inner thread for you. Okay, and what this enables you to do, because these are completely decoupled from everything, they can be used on their own, you can submodule these in, and this is what the kind of white dotted lines are supposed to be showing. If you've got an application, you can just bring in one library at a time because they're in their own Git repositories. And then you can always fix on a release, or you can just link to the head revision and update if you're doing all your own testing as well. There's a bit of a complex diagram, so I'll try and demonstrate this a little bit better here. What I'm trying to show here then, you get used to these diagrams now, the application code, this is running on, or in this scenario, I'm going to describe this as running on a very small MCU. Maybe it's even 8-bit, and it's managing to do internet connectivity because it's using a modem. And the modem's doing the TCP and the modem's doing the TLS, TLS being the most RAM-hungry thing. Okay, now this is your application, it's connected already. And what you can do there is just submodule in just the MQTT library, and because it's not dependent on anything else other than the C library, I should point out, I suppose, then you can submodule that into your project and get that to use the TCP connectivity that you have already. So this really then enables us, as you can see, to tick off the flexibility. You're not locked into any tooling ecosystem even, and the portability, the simplicity, all of which is going to enable you to be as open and as agile as possible, and hopefully have to change as little as possible in the future. Okay, so the next thing then, business continuity. We're kind of returning to this, we mentioned it before. Business continuity is obviously very important. Your supplier has to be there longer than your products are in the market. Hopefully longer than your business is going to be in the market. And this is really where companies like AWS sponsoring products like FreeRTOS brings huge value to the entire embedded community. Remember, because we've just said that these libraries are independent of anything else. They're independent of FreeRTOS, let alone AWS. And they are MIT licensed, so there's absolutely no restriction on how you use them. Or, the MIT is a license, I suppose you have to comply with that, but the license doesn't really impose any restrictions. Now, business continuity comes from several different areas. Now, of course, there's an awful lot of people who are familiar with FreeRTOS, a lot of engineers who use it already. There's a lot of skill sets out in the market. So, that's one reason. Then there is, a lot of third-party support, all of whom has a vested interest in FreeRTOS. They're providing productivity tools, kernel-aware plugins or trace tools, that kind of thing. And then, the next level up, companies like AWS, they obviously have a vested interest in getting people to the value as quickly as possible. So the software is free, right? But we also want to make sure that that software is as secure as possible. And this is an ongoing process. Obviously, it never really ends. And one of the things that AWS are doing is formal proofs on the code. So there's a growing number of formalized memory safety proofs, and some of the algorithms have formal proofs. We've got a couple of blog posts on that. In fact, this diagram is taken from a blog post on the freertos.org site, which is describing these things. So this is adding in that extra level of confidence. And then there are things like the fact that AWS are very well practiced in kind of global best practices in things like incident report, investigating incident reports, patching software, over-the-air updates, and all this kind of thing. All that expertise which has been built up for their all their cloud customers over the years. So that's we also benefit from that. You don't have to be an AWS customer to benefit from these like formal proofs and that kind of thing. And of course, there's the next layer of this confidence, if you like, this business continuity, is the fact that there is long-term support promises on subsets of these libraries. Okay, that's a lot about business continuity. And like I say, the value proposition here is really great. So we take that off as well. Now we're going to come back to probably the most obvious thing that I mentioned already at the beginning, and that is you can't really be future-proof unless you can do an over-the-air update, specifically an over-the-air update of your firmware. Why do you want to do that? Well, there are obvious reasons like security patches, for example. Bug fixes is another example. There are other business reasons as well. Maybe you want to have different pricing models where, as a customer pays for more, then you can update the software with more capabilities. If you think about our motor control, this predictive maintenance, maybe the base is just checking vibration, and then you can unlock temperature monitoring or the current draw of the motor and all these things. You can improve your software over time by actually adding functionality in there and making sure that you can stay ahead of the market. So lots of reasons you want to do this over-the-air update. Now, the reason I said this is a bit of a two-way door decision. Although I'm showing AWS specific over-the-air update here, you can of course send a new image to your device that from that point on gets it to use another over-the-air update service, of course. So this doesn't really lock you in. Obviously, AWS and other cloud services have their unique value from OTA. This particular screenshot shows you how the AWS OTA service is actually fully linked into the other device management services. The reason I say that shows you is because here you have a choice on this kind of radio button. Do you want to use a new image that you're going to send to your device which you have signed already? Or do you want to use an image which is unsigned, and get AWS signing service to sign it for you. And of course, signing your image for over-the-air update is very important, so the device knows that only the handful of people that probably have access to the signing certificates are the people who have signed it, and it's not been tampered with since. Okay, so that kind of completes the criteria check-offs here. And we can come to our conclusions. So our conclusions are basically that embedded software is getting more complex, no doubt about it, and it will continue to get more complex. So our investments in developing this software are going up, but we want to manage that cost as much as possible. A fantastic way of doing that is to make sure that we are always thinking about our efforts in the future, to make sure that we're not locking ourselves into something. We've got access to the source code, we can update, et cetera, et cetera. I'm not going to repeat everything that we've just been through here. And ultimately, that investment will just get a return on again and again. Great. So once again, thank you for watching. I am naturally going to invite you to come to the FreeRTOS.org site. There you will find links to the reference integrations, either FreeRTOS reference integrations, AWS IoT reference integrations, which are in the device catalog, which is on the AWS site, but you can find links to it. And you can also find links there to partners as well, the special tier partners, either AWS partners or FreeRTOS partners. Come to the GitHub, get involved, see what we're doing, can see what we're working on. I'd love for you to get involved. You can also go to the support forum. We like to be as open as possible, so you don't need an account. You need an account to post, but you can use your GitHub account rather than use a FreeRTOS account if you want to. And that's it. We'll leave it there. Thank you very much.